So we want to compare the results in our previous case. You see, you found the probability that x bar, that is the mean of 5 trout, was between the mean length of 5 trout was between 8 and 12, as opposed to a single trout between 8 and 12. That was for a single trout. This is the mean of 5. So why is this? Why are these different? Both x and x bar have a normal distribution. Both have the same mean of 10.2. The difference is in the standard deviations. For x, the standard deviation for x is 1.4, whereas the standard deviation for x bar, there is a change in formula. You take the original one, divide by square root 5. Look, square root 5 is a number that's 2 point something. Now the same 1.4, if I divide by 2 point something, my standard deviation is going to be even smaller. All right. So the picture here is as follows. This is for my original x. Look how spread out it is. Why is it spread out? Because standard deviation is 1.4. Now here is distribution x bar. It is not spread out. It's scooped up around the same mean. Mean is 10.2 here, mean is 10.2 here. It's scooped up here. Why? Because the standard deviation is much smaller, correct? So in other words, the curve, the data is not spread out. If standard deviation is small, as the name suggests, deviation is small, means most of the data is within the mean, close enough to the mean, and that's why it's all scooped up. And therefore between 8 and 12 you have lot more data here than in the previous case. The data being spread out means between 8 and 12 you have much less data. Only 84% data lives here, whereas 99% data lives here. Okay, so change in standard deviation does this. So when we are looking at x bar, you usually have smaller standard deviation around the same mean, and that's the point of central limit theorem. Okay, more data gets scooped up around the same mean. So we see that both curves use the same scale on the horizontal axis. The means are the same. The shaded area is above the interval 8 to 12. It becomes clear that the smaller standard deviation for the x bar distribution has the effect of gathering together much more of the total probability. Okay, so therefore the region from 8 to 12 has a much higher probability for the x bar distribution. The standard error is the standard deviation of a sampling distribution. Standard error is the new deviation, sigma of x bar. This is sigma over square root n. Okay, so notice the new standard deviation corresponds to x bar. It is smaller than the old because you are dividing it by something large. Okay, next, the x bar distribution given x follows any distribution. So far what we saw was that x was normal. What if x is not normal? Then what do we do? Now using the central limit theorem to convert x bar distribution to the normal distribution. So go through the same procedure. Mu of x bar is mu, that is the mean of x bar is mu. Sigma of x bar is sigma over square root n. Alright, this is the standardized. All this matters when sample size is greater equals 30. Okay, so central limit theorem, when you are not normal when X is not normal is this one. If X possesses any distribution, then the sample mean X bar based on a random sample size n will have a distribution that approaches the distribution of a normal random. You see the difference between the previous central theorem, limit theorem, and this one. In the previous one, X is normal. X itself is normal. Then X bar is also normal. All right. Whereas here, X need not be normal. X possesses any distribution. Then X bar will approach normal. In other words, X bar is approximately normal, but the mean remains the same. Standard deviation is sigma over square root n, just as before. And this is valid when n is at least 30. Okay. So you want n to be at least 30, greater equals 30. Now here is an example. A certain strain of bacteria occurs in all raw milk. Let X be milliliter of milk. The health department has found that if the milk is not contaminated, then X has a distribution that is more or less mound shaped. The mean of the distribution X is 2500. Standard deviation is 300. In a large commercial dairy, the health inspector takes 42 random samples. So N is more than 30, which is good. So X, you notice they are not telling us that it is normal because we don't know it is normal. Okay. At the end of the day, the bacteria count in each of the 42 samples is averaged to obtain the sample mean bacteria count X bar. Okay. Assuming the milk is not contaminated, what is the distribution of X bar? Well, sample size is 42. Since this value exceeds 30, central limit theorem applies, and we know that X bar will be approximately normal, with its mean to be mu, the same mu as before, and its standard deviation sigma X bar is sigma over square root n, which is approximately 46.3. Notice the original sigma is 300, but I'm dividing by square root 42. So that comes to the new sigma will be approximately 46.3. Now use this information. Assuming the milk is not contaminated, what is the probability that the average bacteria count X bar for one day is between these two? So you want X bar to be between these two numbers. So convert it or to a standardized score using this formula. All right. So X bar, when I apply this formula, I get Z. I'm going to apply the same formula for these two numbers. These two numbers over here, right? So, and that gets you negative 3.24, and this one gets you positive 3.24. So the probability that X bar is between these two numbers is same as the standard score being these two numbers. Find the area corresponding to the big number, subtract area corresponding to the small number, and you get this particular probability. The probability is 0.9988 that X bar is between these two numbers. Okay. Now, interpretation. At the end of each day, the inspector must decide to accept or reject the accumulated milk. All right. Suppose 42 samples taken by the inspector have a mean bacteria count X bar that is not between these two numbers. If you were the inspector, what would your comment on the situation be? Well, the probability between this and this is that is not contaminated is very high. Okay, so to be not contaminated is very high because you see we got 99% probability you're not contaminated. Now, if the inspector finds that the average bacteria count is not between these two, then it is reasonable to conclude that something is wrong with the milk. You're below this or above this, then something is wrong with the milk. If X bar is less than the lower number, you might suspect someone added chemicals to the milk to artificially reduce the bacteria count. If X bar is above 25, 26, the higher number, you might suspect some other kind of biological contamination. So you see, to fall between these two numbers, probability is 99%. So if you are below this or above that, something is off. That's what the inspector will conclude. So how do we find probabilities for X bar? Well, suppose you are given an X where n is sample size, mu is the mean of X, sigma is the mean of X. If X is normal, then X bar is normal. If X is not normal, then you want sample size to be greater equals 30, then X bar is approximately normal. All right, so these are two important things to think about. Once you have that, convert X bar to standardized score using the standard formulas, and then use the standard normal distribution to find the corresponding probabilities. All right, so this completes lesson 7.5 theory. Next videos will cover problems on lesson 7.5. Until then, bye.